great to have you here, Yann, just in time. Or, well, a few minutes late, but anyways. So today we'll talk about embodied AI. I know that's a topic that you're passionate about. Also a topic that I'm also quite excited about. Actually, both of us, I think, for many years. But I think now a lot more people. This is really kind of coming. There's a lot of excitement, a lot of investments, a lot of things going on. And so I think we'll dig a little bit deeper in what's already possible, what we see on the horizon, the gaps that we see, the kind of things that are needed, et cetera, et cetera. So maybe first, embodied AI, what are we talking about? So it's really, AI that can actually perceive in the world, understand the situation, be able to reason about that, plan based on that, and then act in the world. So that's really what we're talking about. This can go from self-driving vehicles to then also, humanoid robots and things like that, and anything in between, I would say. So Yann, like maybe we can start, where are we today? Like what can we do, what can't we do?
So we're not very far. We have, so first of all, it's not just embodied AI in the sense of robots and things like that. It's also disembodied physical AI, AI for the real world, right? So there's a lot of systems in the world that need to be understood, predicted, controlled, which are not necessarily bodies, right? It could be a manufacturing process, could be a turbojet engine, it could be any kind of industrial process, anything that's physical, anything for which the data comes to you in the form of a sequence of high-dimensional, continuous, noisy signals. Video is the best example. Proprioceptive sensors on a robot is another good example. But there is a lot of applications of this that have nothing to do with robotics, right? So it's anything that is not language-related. That's really the better definition, right? So the real world is fundamentally different from language, and the reason language has been, like LLMs have been so successful is because language is easy. We have systems that can pass the bar exam. I'm not going to say they are as smart as a lawyer. I don't know if there is any lawyer in the room here. No, we're all scientists and engineers here, so I can say that. So we have systems that can pass the bar exam. They can also, do math, right? So equations, they can write code. Many of us here write code too. But they don't really deal with the real world, right? Which is the reason why we don't have domestic robots, we don't have level 5 self-driving cars still, at least not at the consumer level. And so, humanoid robots.
Level 4, but not level 5.
Not level 5. And even the level 4, we cheat a lot.
I think level 4, so Waymo, I think you can claim that they achieve level 4.
They do.
But not level 5. They need full maps, they need control of where they are and when they operate.
And they need, exotic sensors, LiDARs, and complete
But that's okay, that's okay.
It's fine, you can cheat. Okay. It's perfectly fine.
I don't think that's cheating, by the way.
No, I mean, it's okay. But it's expensive in the sense that how is it that a 17-year-old can learn to drive in, 10 to 20 hours of practice? And we have millions of hours of training data that we could, in principle, train a machine learning system by imitation to imitate human drivers. But that doesn't work. You don't get reliable driving systems this way. And so that sort of leads me to another statement about robotics. There's a lot of companies building humanoid robots, and they do those kinds of, they play kung fu and, impressive things. This is all pre-computed, okay? None of those companies, absolutely none of them, has any idea how to make those robots smart enough to be useful, right? That's a big secret of robotics industry. You can train them on very narrow tasks, and you have to collect lots and lots of data, the same way people thought they would build self-driving cars. And it's expensive, and it's only practical for a small number of narrow tasks, and you don't have robots that have nearly as good as a common sense as your house cat, let alone human intelligence, right? So that's the that's the challenge for the next few years, right? Getting systems to really understand the real world. And the problem is that the approaches that have been successful for language do not work for high-dimensional continuous noisy data. You have to use something else.
So, so let's actually start with, with what people are trying now in robotics and in embodied AI. So, and I know your positions on LLMs and what you can do with them. I agree with you. Language is easy because, in a sense, we immediately start at the semantic level. We have, tokens are essentially very close to like a semantic concept. And so directly by working at that level, we can ignore a lot of the noisy, complicated, real-world kind of things. We say car, and we can imagine many, many different things and so on. But for an LLM, it's just kind of a car with some dimensions with it, but kind of some concepts associated with it, but like no understanding what it actually is, right? Just having correlations to other stuff. Anyway, so there's LLMs, there's VLMs, and there's VLAs now that there's a lot of excitement around, right? Well, not by you, but by others. But I'd like you to a little bit kind of explain like the relationship between all of those three, and also where you see the shortcomings there.
Right. So VLM is basically the idea of mixing in visual representations together with language, with tokens that come from language, and then use the machinery of LLMs basically to do that. VLAs are kind of a version of this where the output of the system is a sequence of actions. There's a major flaw with those approaches, and they're extremely difficult. It's extremely difficult to make them work. The VLAs, or so-called agentic systems, only work in situations where the actions obey a script that you have to basically repeat all the time. Repetitive task of some kind. So it's a new way of just designing, automating a task, which is data-driven instead of being, programmatic. But it's very brittle. It's very restricted to very narrow applications for which there is a script that you can follow. That's not what you want. You want a system that can accomplish a new task it's never been trained to accomplish, which every human is capable of doing, every animal even, facing a new situation, using their mental model of the world. Okay, so here we're going to talk about world models. World model is a big buzzword now, but mostly, but people mean different things for this, and it's mostly a buzzword in research, not so much in industry. The AI industry is completely LLM-pilled, as they say. And in Silicon Valley, everybody is working on the same thing. They're all digging the same trench. They are stealing each other's engineers so that they can't afford to do something different, because if they start going on a tangent, they're going to fall behind the other guys. And so they're all doing the same thing. And it's one big reason I left Meta, right? Because Meta also became LLM-pilled, with sort of recent reshuffling. And it's fine, it's a strategic decision that maybe it makes sense for them, it's just not what I'm interested in. And so I cannot imagine that we can build agentic systems without those systems having an ability to predict in advance what the consequences of their actions are going to be. The way we act in the world is that we know we can predict the consequences of our actions. And that's what allows us to plan. So what is a world model? Given the state of an environment, a system you want to control at time t, and given an action or intervention you imagine taking, can you predict the state of the world or the system at time t+1? If you have, that's a world model. You don't do this at a pixel level if it's video. You do this in an abstract representation space. And that's a crucial key insight that you need to really understand. You cannot predict every detail, for example, of what is going to happen in a video. I can take a video of this room, rotate the camera, and stop here, and then ask the system continue the video. System will predict, we're in a room, there's probably, a door at some point. There's no way you can predict what all of you looks like. There's absolutely no way in hell you can predict the texture of your beautiful dress here, which is, very shiny and which has, a huge amount of information. It's just impossible, right? So if you train a generative architecture, which is supposed to predict at the pixel level, it fails. It doesn't do anything useful for you. I mean, it might produce cute videos or cute pictures with diffusion models, but that's it. And it will not understand the underlying structure of the world. For that, you need to find an abstract representation of reality that allows you to make predictions and eliminate all the details you cannot predict.
And we'll come back to that. I first want to take a step back to to the VLM and VLA world and LLM world. I think you said like you can only do things that are essentially scripted and this and that. But I would say in industry there are many things that are useful and that are scripted, and you have to carry out a certain task, and most of the time you have to do it. So I would say there is probably a lot of potential for this current technology to actually deliver value with today's state. Like if you look at VLMs, essentially it's text, and I agree it's actually really text first, and then an image is worth 1,000 tokens, literally, pretty much. And then with action, it's you still essentially take a picture. This is the situation. This is what I want to do, and then like from that you kind of, if it's all scripted, kind of in a sense, you can kind of carry it out, right? And you can build. You can program it. It's probably a simpler way to program than maybe what we used to do before. So let's say, like if you would be an advocate of VLAs or so, like what do you think we can all achieve already with what we have today?
Well, I mean, it's like LLMs. Those things are useful. And there is probably a number of applications, probably relatively narrower than what people are thinking, for which those things would be useful and practical and deployable. But, I'm old enough to remember what happened in the 1980s with expert systems. Okay, expert systems, you were going to, the coolest job at the time was going to be a knowledge engineer. You're going to sit down next to a human expert and then translate the knowledge of that human expert in rules and facts. Okay, and then use a inference engine to basically replace the expert or, kind of clone the expert if you want. No machine learning whatsoever, it was entirely human. That approach to AI essentially failed because the brittleness of the resulting system and the cost of this knowledge transfer into a machine was just too high. So there was a very narrow number of applications for which it was practical. It's going to be the same thing for VLA. There's going to be a relatively small number of applications where you have scripted scenarios where those things are going to be useful. But in the end, if you are interested, like I am, in building systems that have the intelligence of, let's say, a cat, let alone humans, you need common sense. You need the ability to predict the consequences of your actions. You need the ability to plan. You need the ability to reason. And you're not going to get this with VLA or VLM or LLMs or any generative architectures.
I agree, but I would say, I see a lot of potential industry of just, doing what you're supposed to do.
They're useful. I mean, LLMs are super useful for coding, no question.
Okay, so back to to world models. So you said like you need to maybe not predict at a pixel level. Now sometimes you can. I mean, like video models actually do very nice work. In particular, when say like with a VLA, when you're given a starting position. This is the situation, and I have to predict now. I just need to do a relatively simple task. I need to move a few things around, kind of assemble something or so. There I can probably predict at a pixel level exactly how it should look like, right? So I think sometimes, there are situations where you can actually go to the pixel level. I know, of course, like you're a strong proponent of all the JEPA framework of going to, I agree with you. You don't have to predict every pixel for most situations. I think sometimes you do, like when you really want a fine scale thing. In the end, you might need detail. My question is actually where. How do we find, what is the right level at which we, and I think it's not always the same necessarily for every task, so what is the right level of abstraction at which we need to predict? I mean, we as humans, we do indeed always, or our whole brain is essentially dedicated to predicting the future. And then we look at the differences, right? And we might care about them or not. And indeed, I think we actually don't predict, I think even most of the JEPA, maybe I'm wrong, but is predicting at a certain level of abstraction. Most a fixed level that's learned of abstraction. Intuitively, I would actually like to be able to predict throughout the levels and go to the level I want.
Yeah, totally. No, I mean, picking the right level of abstraction is absolutely essential to understanding the world around us. In fact, we don't know any other way of doing it. It's something that, not many people realize, but let's say I want to plan a trip from New York to Paris. Let's say I'm sitting in my office at NYU, it's midday, and I want to be in Paris tomorrow. I cannot possibly plan my entire trip to Paris in terms of elementary actions for humans, which are millisecond by millisecond muscle control, right? Because it's too complicated of a planning issue, and I just don't have the information. I don't know if someone is going to run into me when I walk to the elevator. I don't know how long I'm going to have to wait for a taxi, right? So I cannot plan, but I can plan at a very abstract level. At the abstract level, I can say, well, I need to go to the airport and catch a plane. Okay, now I have a sub-goal, being at the airport. My new objective is being close to the airport, right? I'm in New York, so I go down the street and hail a taxi. Okay, that's a 2-action plan, but it's very high level. Very little information I need to know, other than maybe the condition of traffic. It would determine whether I take a taxi or subway or helicopter. Then how do I go on the street? I go to the elevator, push the button, walk out the building. How do I go to the elevator? So at some point in the hierarchy, you get down to a point where you can just take the action because you know how to stand up from your chair and walk to the door and open the door and things like that, right? So this is called hierarchical planning. It's a completely unsolved problem in AI. People have, mostly given up. But that's basically what really is a big challenge that we should crack for kind of future AI systems that can behave properly. Animals do this all the time. Humans are much better at abstractions than humans, but animals do this. So that requires a multi-level world model, right? A low-level world model that predicts short-term with a lot of details, with low-level actions. Okay, if I send a particular command to my muscle, it's going to move my arm in a particular way, right? Or high-level actions, hailing a taxi to go to the airport, that's more of a high-level action. The low level is not describable in language. Some part of the high level is, and if it's a normal script, maybe VLA will do something like that. But really what you need for all of this is a mental model that allows you to predict what the consequence of your actions, regardless of the levels, are going to be. So how do you train a hierarchical model of this type? So first of all, you have to realize that you cannot make prediction in pixel space, in input space. You have to make prediction in that abstract representation space. And when you train that, so this is the JEPA architecture that Marc was just mentioning, right? So JEPA means Joint Embedding Predictive Architecture, and it means learning an abstract representation of the input signal and making prediction in that abstract representation space and training this whole thing at once. And the prediction might be conditioned by an action that you imagine taking, which gives you a world model. So the abstraction level that this system is going to learn depends on the horizon that you train it to make predictions at, right? If you train a system to make prediction, 10 milliseconds in the future, it's going to make very accurate prediction in the short term. Those predictions are going to diverge from reality really quickly. So there you have to go one level up, maybe predict 1/10 of a second or a second in the future. And then the higher you go in the hierarchy, the longer term the predictions are. I could, in principle, describe everything that is taking place in this room here between us in terms of quantum field theory. All right, that'd be crazy, but it would be a very accurate description of everything that takes place here, including the neurochemistry of our brain processes and what we think and everything, right? But it's completely impractical. I would need to measure the wave function, of this room and probably like a cubic kilometer around us. And then use some ridiculously powerful quantum computer to actually do the simulation. Like, we don't do this, right? So we invent abstractions in science, but also that's what we do when we perceive and understand the world. We invent abstractions like particles, atoms, molecules in the living world. It's proteins, organelles, cells, organisms, societies, ecosystems. And the right level at which to describe what's going on in this room now is, psychology, economics, and science, right? It's pretty high in the hierarchy. We're not going to predict, the reaction of all of us in terms of particle physics. That's impossible. So being able to ignore details that are irrelevant, that you cannot predict, so that you can make long-term prediction is absolutely crucial to intelligence. And generative models do not allow you to do this. This is what JEPA enables.
But JEPA at this point still is typically for a particular task, it learns a particular level of abstraction that's...
Well, that's what you see in publications, but...
Okay.
We're working on multi-level hierarchies.
Okay, so in terms of, to act in the, in the physical world, what are the sensing modalities that, that you think we need? So like now we narrow it down a little bit to like, maybe more like really robotics applications, right? What do you see as kind of useful we both have a background in vision or so we of course will use cameras or vision sensors, but what else is needed to make things work?
So what is what would be the appropriate world model for a robot? There's several components. There's first a model, sort of mechanical dynamical model of the robot, which you apply a torque to a motor in one of the joints, right, and the arm or the legs move in a particular way. You can actually write down such dynamical models with a bunch of equations. This is what classical robotics is about, and you can use this model to do motion planning to some extent. It doesn't work that well actually for complex actions, but all of those videos of kung fu playing robots, that's what they do. It's all planned in advance using handwritten models. They're fine-tuned a little bit using reinforcement learning and stuff, but it's kind of a minor step. But then there is the model of the world around the robot. Can you predict what other people are going to do? Whether this object is about to fall? Can I catch it? Things like that. So it's a model of intuitive physics. How do you learn that? We learn that as babies by watching the world go by, and it takes 9 months for a human baby to learn gravity, to learn that objects that are not supported fall. 6-month-old babies haven't yet integrated the idea that objects, don't float in the air. But 10-month-old do, by that time they have. And so we acquire in the first few months of life all of those basic concepts about the world. The world is three-dimensional. There are objects that can move independently. There are, objects that, move that are not animate, and so they follow certain rules. There is, categories of objects. We don't need to give names to them. We know the difference between the table and the chair. And then, objects have inertia, conservation of momentum, things like that, right? So we learn this intuitively. Can we train a system from video that will acquire this type of common sense that, animals learn in days and humans months? And the answer is yes. So we have those video systems, those JEPA architectures, right? And, and we determine the level of abstraction at which we train them. So they learn a representation of the video from a window of 64 frames or something like this. And they're trained, you take a piece of video, you corrupt it by masking a piece of it. And then you run the full video through an encoder, run the corrupted video through another encoder, and train a predictor to predict the representation of the full video from the partially corrupted one. And you train the whole thing end-to-end simultaneously. And the system comes up with a good abstract representation of the world that only contains the information that is predictable. Okay, and it only predicts the information, the part of the world that is predictable is going to ignore all the noise and details of texture of your dress. Although it should not ignore that actually. And this kind of detail. And so that's really the way to proceed. We've trained this model, so it's called VJEPA2, V for video, and it was trained on the equivalent of 100 years of video. That seems like a lot, okay, because it doesn't learn as much as
almost no human
as a 2-year-old.
That much.
No, it certainly doesn't learn for that long, and it's not a lot of video. It's about a day of YouTube uploads. I mean, we have like enormous amounts of video. If you put a number on it, it's about 10 to the 15 to 10 to the 16 bytes at 2 megabytes per second. This is 100 times more than the biggest LLMs, okay? Because there's not that much text on the internet. It's only about 10 to the 14 bytes. And so using video, you can train with way more data than any LLMs, which is why we're never going to get to human level intelligence by training LLMs or by training on text only, right? We need the real world. Okay, so you train the system on 100 years of video, and then we can test whether those systems have acquired some common sense. So you show them a video where something impossible happens. This is, by the way, how we test babies to figure out if they've learned a particular concept like gravity. You show babies a scenario where like a little car is on on a platform and you push the car off the platform and the car appears to float in the air. 6-month-old babies don't pay attention. 10-month-old go like this. And I pay attention to it because, we're programmed to pay attention to the violations of our prediction of our internal world model. That's how we know we have a world model. Yeah. And that's how psychologists test that. And so we can show a video where something impossible occurs, like someone threw a ball in the air, and the ball stops, or it changes shape to a cube, or it disappears. And the prediction error goes to the roof when you run the model on it. Because the thing says, I didn't predict anything like this, that's impossible. And so that's the first time I've seen any kind of model that has some level of common sense. And I think it's, going forward.
But I think if you run it through a video prediction model, those scenarios, as you say, if you have the starting position and you see it happen, you could also run it at a full pixel level, and you would probably very nicely also there be able to measure that suddenly there's a discrepancy with what your video model predicts and what what you see in the video.
I hope you'll pardon my French, but absolutely no way in hell.
No, I don't agree. I think so. If you have the starting point of the video, and you run from that frame, you run it forward. So you have a few frames, and you run it forward. The video model, you will suddenly see that there's a big deviation between what you predict at the pixel. Now it's only because you have the starting frame and this and that, but you could also predict. Now I agree with you that this is like complete overkill for the task. But I think you can also do it. You can essentially do it up to the level that you don't have enough abstraction anymore.
It simply does not work. We've tried to do this. I've tried to do self-supervised learning from video for 15 years. The first 10 years, I tried to use generative models with latent variables. Okay, and the best method that we have to do this today is diffusion models. Mm-hmm. And with this, you can produce cute videos. There's no question. It never worked for natural videos. It worked for stylized videos, like video games. Basically already abstract representations of video, or like segmentation maps, to some extent. But it never really worked. And the reason it doesn't work is because there is an infinite number of plausible things that can happen in a video. And when you train the system to make predictions at the pixel level, the best thing it can do, it can't represent a distribution of all possible frames. And so the best thing it can do is, produce an average of all the possible features. So if you use diffusion models, you get around that problem, but not entirely, because your predictor can be completely mode collapsed. So it will produce a nice video, but it's not going to understand the underlying dynamics. So why do we know this? We know this because we have lots and lots of empirical evidence of training generative models for image representation. Okay, so here's a very good example, which works great for text, doesn't work for images. I mean, it works, but not well. You take a piece of data, you corrupt it by masking a piece of it, similar to what I was describing earlier, and then you train some big model, basically an autoencoder, to reconstruct the full input, whether it's text or images. In the context of NLP, that's called BERT. In the context of images, that's called MAE, masked autoencoder. And you do get some representation of the text or the image. For images, though, it's very expensive to train, and the representation you get out of it sucks. It really doesn't work very well. The method that produced the best image representations are all joint embedding architectures, which means architectures that are trained without a criterion that attempts to reconstruct pixels. You have to allow the system to ignore information that cannot be predicted. And if you put a reconstruction criterion, it will have to reconstruct everything, and you kill it by doing it. And we know this. We have lots of comparisons of MAE with Dino. So you know about Dino. Probably the best method for self-supervised learning of image representation. Probably the best method for feature extraction. Whatever, right? Whatever method you use. This beats supervised learning now, right? Self-supervised learning for images with joint embedding architecture beat all approaches to supervised learning, even those for which we have tons of data. This is new, only happened in the last year. So Dino is one of them. IJPA is another one. There's a bunch of, a small number of methods like this that, beat generative approaches for image representation. And there's tons of benchmarks for which we have images. So I started realizing this about 5 years ago, and basically started, kind of bashing generative models and completely kind of try to brainwash everyone into abandoning generative AI, which is difficult because, everyone talks about generative AI as the thing, it did make me very popular among some of my colleagues who work on LLMs.
So, so coming back to trying to solve robotics, you mentioned a little bit reinforcement learning. There's a big fan of unsupervised learning. There's also supervised learning. Let's say in the mix of those different things, like they probably have to work together in some way, right? Like you want to figure out how the world works, probably unsupervised. You want to learn how to kind of do some tasks. That's probably has some supervisory signal for sure. And then, reinforcement learning is probably the thing that actually gets it all to kind of, fine tweak and kind of all the actual moving parts of the robot and so on. So how would you kind of see those things coming together?
So about 10 years ago, whenever I give a talk, I would show a slide with a cake. All right, I'm sure some of you have seen it. Who has seen the cake? Okay, great. That was about 10 years ago. And the cake is an analogy. I was trying to make the point. Everybody at the time was like completely into reinforcement learning. I was telling people like reinforcement learning is so inefficient in terms of samples. It's never going to amount to much, except for games. Because for games, you can generate so much data that it's fine. And that turned out to be true. Okay, so the bulk of the cake, the genoise of the cake, if you want, is self-supervised learning. You learn about the world, you learn to represent it, you learn world models, you learn prediction. That's self-supervised. You don't need to observe an expert, you don't need to learn from anyone else, you just observe the world go by, okay? That's the bulk of it. Most of your parameters or whatever, your intelligence, most of what you learn this way. Then there is a thin...
And by the way, that would also be embodiment agnostic.
Sure.
Would be, yeah.
Yeah. Then there's a thin layer of either supervised learning or imitation learning or behavior cloning or inverse reinforcement learning. There's several names for it, but it's basically trying to imitate or reproduce behavior of an expert, right, or human. That's a thin layer. Most animals never go through that phase because they never meet their parents. So, like octopus never meet their parent. They get really smart in just a few months. They live only 2 years. And then there is the cherry on the cake, and that's reinforcement learning. It's just like minor fine-tuning because it's so inefficient. Like if you were to train a self-driving car from scratch to learn to drive, it's completely impractical. People thought this was a possibility, back 10, 12 years ago, and realized quickly that that was completely impractical. It would require too many trials. A car, driving next to a cliff would have to run off the cliff a few thousand times before realizing it's a bad idea. And then a few other thousand times, it's very dangerous in Switzerland, and then a few more thousand times to realize how to not run off that cliff. And then you're next to another cliff and you have to do it again, right? Because it doesn't necessarily transfer to the new situation. So, reinforcement learning in the real world.
If you had learned at the right abstraction level, you might have been able to generalize.
Yeah, but then this abstraction level is given to you by self-supervised learning, right? So
yeah, but you can build on top of it, let's say, like.
Sure. Yeah. No, I mean it's necessary, right? I mean clearly we adjust our behavior, from action we do in the world, and we realize we're not doing it right. So yeah, that's a required cherry, but it's only a minor.
But then, I have some colleagues that are kind of big in reinforcement learning, and the way they do it is they use simulation to do it. And of course, there's still a little bit of a gap, but they get kind of robots with all kinds of things. Kind of they figure out their gait and this and that, and they and of course there's the gait of just walking on a flat surface. That's pretty. You could design that. But then they also figure out how to kind of crawl in very interesting ways, from over things and so on. So simulation is a thing that a little bit decouples that cost. There's still a cost to simulation, but it's not the same cost as actually throwing the robot off the, the bricks or, down the cliff or whatever, right?
I mean, for any particular set of tasks or domain or engineering problem, you're going to have a really specific solution to it that's going to, solve the problem. Which is why, we have 30-euro gadgets. They can beat us at chess, but they're not necessarily intelligent, right? So same thing here, right? We can cheat our way out, or we can engineer the hell out of it, and solve problems of this type. So I mean, to train a system by reinforcement learning to control a humanoid robots, you basically have to simulate thousands of copies of that humanoid robot in parallel on supercomputers, have them do all kinds of stuff, and still in the end,
thousands you might do on one GPU, but
that's right, possibly, maybe more. Well, not if you have perception; that would be more expensive. But
sure.
But in the end, they will only be trained for this particular task, this particular environment, and it'll be brittle. A much more efficient way to approach this is this idea of training world models. So ask a 10-year-old who has never done it before to accomplish a new task, and 10-year-old tend to accomplish new tasks pretty often. But ask a 10-year-old to clear out the dinner table and fill up the dishwasher. 10-year-old can do it the first time. Doesn't need to be trained for it. It might become more efficient at doing it if it does it multiple times, but can do it the first time. Why? Because of a world model. Same thing for the 17-year-old learning to drive. The world model allows the 17-year-old to predict that if driving next to a cliff and turn the wheel to the right, the car will run off the cliff and nothing good will come out of this. That's a world model. That's what allows us to solve a new task zero shot without being trained, or to learn new tasks like driving extremely quickly, or skiing, right? Same thing. First time you ski, you're kind of hesitant and you kind of think about everything you're supposed to do, and then you become familiar and it becomes kind of second nature, but that's the second phase, right? That's the difference that psychologists call this system 1 and system 2. System 1 is tasks that you can accomplish automatically without thinking. System 2 is you use your mental world model, that's all your prefrontal cortex essentially. And then you accomplish, you can plan what actions and you accomplish that task.
So for unsupervised learning, I think you can learn from corpus of data, kind of understand how the world works and so, but still translating that to a particular embodiment, there are challenges there, right? Like, because there you don't have an unlimited amount of data anymore to kind of just learn basic principles of how the world functions and so on. So how do you see that kind of connection to the specific embodiment, to the, like people train something on one embodiment and then have to transfer it to another embodiment, and you have to start all over. So like, not for understanding the world, but for understanding how you kind of do something in the world. Okay, so here's the experiment we did with VJPA 2. And we have a new version coming out, VJPA 2.1, soon. So VJPA 2, you pre-train on these 100 years of natural videos, right? And the system learns to represent video. It learns to fill in the blanks in the video. That's the first phase. Now you have a really good representation of physical reality and a good abstract representation and an ability to predict, but not action conditions. So it's not related to any particular embodiment, or there is no robot arm the system is controlling. So there's a second phase where you fix the encoder and you fine-tune the predictor and you add an input, which is an action, right? So you have position of the robot and state of the world, an action that you observe, or that you send to the robot, and then you observe the state of the world and the robot right after. That requires two submodels, a model of the robot itself and a robot of the environment, and then maybe a model of the robot itself, a model of the environment, because the environment might evolve by itself, and maybe a model of the interaction between the two, right? So if I move my hand here and I close my hand, nothing happens, okay? That's not completely under my control. But if I move it around the glass and I close my hand, now I pick up the glass. So that's an interaction between the environment and the thing. The system has to model all that. Now, it turns out that fine-tuning phase, where you have state, action, next state, does not require that much data. And the data you can obtain through simulation. But it's not a simulation of a task, it's a simulation of just the dynamics of a system. So you don't need a huge amount of data. And the model that you get at the end is generic. You can use it for any task. So now you can use that for planning motion of a robot to actually pick up a glass or pour water into a glass, and it actually works. So let's switch to something else. Like I want to first go back in time to when computer vision started working. At least the geometric parts are working long before that. But let's say the semantic understanding of the world. I would say that's essentially CNN started making that work about 15 years ago. So there we had a very useful, clear inductive bias of, hey, like if I see something here or there, it doesn't matter. I want the same filters, the same thing, the same understanding. So are there things like this? Then there's also, of course, the bitter lesson that's saying, like, forget all of that, like if I see a cat up there, it's probably like a floating cat, so it's something very different than when I see it. I should not see a cat up there, so I suppress that, and so I don't want the same filters up there that I want them down there, and stuff like that. And so eventually, if you have enough data, like forget about all these inductive biases and so on. On the other hand, I'm very frustrated in robotics, like this is now with VLA and stuff like that or so, but indeed a big part of the field is like, okay, I've trained this VLA with like a camera up here and like my arm's exactly up there and this exact configuration. And actually, by the way, I have a fixed background. Nobody can, this wouldn't work here. I need the exact background, the exact pixel, by the way, indeed, in their cases often, which is completely silly, but essentially, a lot of that is essentially perfectly predictable with, we have methods to kind of, transfer that to predicted and so on. Where do you see are there inductive biases similar to what we had with, with the convolutional kind of shift in variance essentially that we're bringing in? Like, are there similar things that you see on the horizon or like things that could be applicable for the things we're trying out now in embodied AI?
So you can always, as you say, you can always replace inductive biases in your architecture or prior knowledge in your architecture, like convolutional nature, by more data. And if your training is mostly self-supervised, perhaps you have essentially from video you have an infinite supply of data, more data that you can manage. So maybe there the type of prior knowledge that we put into encoders like the convolutional nature are no longer necessary, and we see this in the. Okay, here's an interesting piece of data. In the academic world, in the publications, the best computer vision systems, most of the papers use transformers, vision transformer, VITs, or some variation of it. Video, not quite the case, because transformers on video start to become really expensive if you want to do high resolution. But you can get the same performance with convolutional nets, and you will get it with less data. But if you have data, why would you kind of take the risk of getting a lower performance? So there is very interesting work by my NYU colleague, former FAIR colleague, actually, Signing Che, something called ConvNext. So he sort of carefully fine-tuned all the tricks, in the convolutional net, transposing some of the tricks I use in transformer, and say, look, you actually get, the same performance with convnets as you do with transformers if you do all the right tricks, if you spend the same amount of effort on them. So there's nothing really intrinsic about the architecture there, at least for images and certainly for video. The thing is, it starts getting impractical when you deal with video. If you have, high resolution video, high frame rate, then the number of tokens that you need to feed to your transformer for that becomes sort of impractically large. And so then the computation is ridiculous. And here is a piece of data that's important. Every single real-time vision system uses convolutional nets. They don't use transformers. Your self-driving car has, in Europe, every car sold in Europe has to have a automatic emergency braking system. And it's a camera looking at the windshield that stops the car when there is an obstacle. Most of them have something that allows you to drive more or less automatically on the highway. Every single one of them uses convolutional net, every single one of them, because you need real time, and you're not going to get that from transformers, at least not today.
So, if we look at, we're also embodied, obviously. We have our brain up there that's helping us figure out how to act in the world. We're using, 20 watts of power for doing that. I think part of it is really to have a very adaptive, level at which we actually read out the, abstraction level and so on. But what do you see on the horizon? What are the kind of things that can bring us, or what is still missing actually? What are the things that we should, as maybe a research community, really focus on to get to something like that?
It's a hardware issue. It's actually a device issue. It's not just a computer architecture issue.
You think the algorithms are solved?
I mean, I think the algorithms are not the issue, the main issue for like power consumption. Here is the problem. In the brain,
the weights are in place. The weights are in place.
The weights are in place, right? Exactly. So in the brain, you know, the number of parameters in a neural net is like a synapse in the brain. It's not quite the same analogy, but let's make this assumption, right? So we have one physical synapse and one physical neuron per virtual neuron, if you want, okay? Whereas in a computer implementation of a neural net or a deep learning system, we reuse the same piece of hardware, the same silicon, to compute the output of multiple neurons and multiple synapses, okay? So what that means, and the reason we need to do this is because our fabrication technology is too big and too fast. So we have to use what's called hardware multiplexing. You have to reuse the same piece of hardware to compute multiple parts of the neural net. And what that means is that you have to get data from memory and shuffle it through the computational engine, right, and put the result back to memory. All the energy, all the power is spent getting data from the memory and writing it back. So the difference between a classical CPU and the GPUs that are optimized for neural nets is that the GPUs have this kind of hierarchical memory that allows to kind of minimize the amount of traffic to memories that is far away and slower, so that you save quite a bit of energy. But you cannot, with current technology, you simply cannot have one computing device per neuron or synapse in your neural net. You would have to go to like some sort of exotic analog technology for this, which does not exist. You know, it might pop up in the future. It could be spintronics, it could be carbon nanotubes, it could be, you know, whatever, some optical widget. But it doesn't exist at the moment. If you're going to use CMOS, the technology is too big and too fast, and you have to reuse the same piece of hardware for different parts of your neural net. You have to shuffle data. That's where all your energy is going to go.
So in other words, if we could have an analog, asynchronous, three-dimensional stacking of elements, we might actually get there.
Yeah, and you know, possibly, and it would have to be. It wouldn't have to be as fast as our current electronics, because it would be massively parallel, like way more than current systems. But you would need to.
How many hertz do we run at?
Oh, we run at like 10 hertz. Yeah. Okay, in the sense of your retina works at about 15 hertz, which is why, you know, cinema is at 24 frames per second, because you can't see. You know, you perceive the frames as motion, right? And the whole process of going from your retina to your inferotemporal cortex or your motor cortex for reacting to a visual stimulus is 100 milliseconds for perception, another 100 milliseconds to figure out what to do. So your feedback loop, when you see an obstacle on the street and you need to brake, you know, hit the brake pedal for your car, that's like 300 milliseconds, a third of a second, incredibly slow. Cats are faster. Okay, which is why, because they have smaller brains, which is why, you know, they can stand in front of a cobra, and when the cobra starts to attack, they go boom. Right? We can do this as humans. We're just too slow. You know, we're going to require some non-volatile memory storage technology that is incredibly compact. Right? We're talking like, you know, nanometers for you know, a single analog memory type thing, which, you know, biology figured out how to do, but we don't know what to do with current fabrication.
And then the other part, so that would be like, you know, potentially like a frozen brain or something, right? A key thing about us is we can adapt, we can keep adjusting. We don't have to first learn and then, you know, infer.
Well, this thing would have to be, you know, to learn in the loop. In fact, there is this concept that people were, you know, kind of thinking of in the 1980s and 90s, where people were working on analog neural net implementations. And it was the fact that when you start to get to these small devices, the characteristic of each device is different. You have a lot of variability from one device to another on a single chip. And so you can't just program the system with, you know, known weights that have been trained offline, because the characteristic of the components vary so much. And so you have to train the system in the loop with the characteristic of the chip itself, which means that system is not reproducible. It's unique. It's mortal, if you want. Okay, like human brain, you can't make another copy of human brain.
So Okay. So so essentially, what do you see on the is there anything out there on the horizon where not back to the hardware in the 80s or so, but more in algorithmically of bringing learning in the loop for embodied systems or for systems that act in the world and have to keep adjusting, and also partially also based on their own if we get hurt and then we can actually adapt and we change our gate a bit and this and that and so on. What's there? Like, can we expect to see kind of learning systems in the loop essentially come?
I think the answer is clearly yes, and I actually don't think it's a particularly challenging conceptual problem. I mean, I don't think we need to invent anything new to be able to do online adaptation. We do this all the time, right? If you try to pick up an object and you realize the object is like way heavier than you realize. This is actually way heavier than I realized. It's like pretty thick glass, actually. And you immediately adapt. Your world model that predicted how much force you had to apply to lift this object, adapts in milliseconds. This is done actually possibly not entirely clear, but probably in the cerebellum. Cerebellum is a very special piece of the brain that actually has most of our neurons in the human brain are actually in the cerebellum, not in the cortex. It's like 50 million neurons in the cerebellum, only 16 million in the cortex, which is weird. But they, mostly the theories about the cerebellum is fast adaptation to kind of changing situations. So again, also when we observe something that violates our internal model of the world, we're programmed to pay attention to it because, we need to learn from it because that means our world model is inaccurate. Also, it could be a tiger jumping at us, right, that we didn't foresee. It can kill us, right? So we have to pay attention to distortion from prediction.
So that's the cherry, right?
That's not a cherry. That's the adjustment of your world model. It's not supervised. It's completely self-supervised. This is not related to a task.
It's reinforcement learning, right?
It's not reinforcement learning. Absolutely not. It's self-supervised learning. It's, okay, I observed something going on in the world, and my prediction was wrong, and now I wait a little, I observe what actually occurred, I adjust my predictor. It's a JEPA architecture. There's no task to accomplish. There's no reinforcement. There's no value function. Nothing like that. It's just prediction error. Okay? And you adapt your model. And that's generic. It's not task dependent.
Welcome to the AI House Davos. Our next panel on the summit stage will begin in 15 minutes.
Okay, we still have...
I guess we have some time.
Okay, so anyways, I think we have to wrap it up. So maybe to finish, where do you see things like 10 years from now, like in embodied AI in particular, right? In terms of robots, in terms of what can they do and what's still unsolved? So
I'm just starting a new very ambitious company with the idea that we're going to be able to solve that problem within a few years and basically have systems that understand the physical world or any modality you throw at them, can build world models, can use those world models to plan, can build hierarchical world models, so you can do hierarchical planning, and then basically be the blueprint for the future AI systems that are much more powerful than LLMs that we have currently. It's a completely different paradigm. Non-generative, as I said, because it's those JEPAs. Not using autoregressive token prediction, but using planning. Okay, so systems that can predict the consequences of their actions, which I think is the only decent way to build agentic systems, except for very narrow applications. And so I'm seeing a future where this is going to be the next AI revolution. Okay, we're going to have another AI revolution brought about by this, and I'm building a company around this idea and I think it's the right time to do it because we already have results that show that this approach works. We can train from video. We get systems that have some level of common sense. We can train predictive models on top of them. World models, we can use them for planning. And so that points to the direction that, we see a clear path to much more powerful AI systems than we currently have.
When you say they're not generative, they're generative, but across the different level, at different levels of abstraction in a sense.
Well, generative, my definition of generative is that you reproduce the input signals, or you predict the input signal. Here you make predictions at representation level. Okay, that's not generative in my world, but
but I mean, okay, good. Thank you very much.
Thank you.